if you're a human being that's interested in logic, you might want to have a look at it.
Okay, I'll check it out.
Okay, cool. Can I go ahead and get started? Let's do it. Okay, so I just want to quickly finish off the result from last time. So just to reboot it into all of your brains, what I was saying is that we don't need the primitive recursive clause inside the definition of a general recursive function, provided that we include a few extra base cases. So the main argument for showing that was the introduction of the beta function, which is thought of as a computable decoder of sequences that have been interpreted as single natural numbers. Now, what we're doing here is I'm showing that once we have such a function, we can, in fact, get all of the general recursive functions, including those that are defined via primitive recursion. So towards that end, I'm going to let f be such a function. Wait, is it f? Sorry, no, it's h. So let h be a function which is defined by primitive recursion via f and g. So f is describing the base case and g is describing the recursive clauses. Then what we do is we let R be the following relation. So given an m plus 1 tuple consisting of D, which is going to be the sequence encoding all of the different valuations for the primitively recursively defined function h, y is going to be the index that we're interested in, and then n1 up to nm is going to be the input. So that tuple is an element of R if and only if when I perform the beta function that I have in hand, so last week I gave an explicit beta function. So when I evaluate that at d comma 0, I get exactly f of n1 up to nm, so that's the base case. And then also, for all k less than y, beta of d comma k plus 1 is equal to g applied to k beta d comma k and n1 down to nm. So the way that we think about this is all I'm saying is that give me an input to the function h, which is what n1 up to nm is, and then also give me a y, which is the iteration that I'm interested in, then this tuple is an element of this relation if and only if d is an integer that represents that sequence of evaluations that I just described. So you can see that I've mimicked the definition of a primitive recursive function inside the definition of this relation. Okay, great. And then once I have such a thing, I'm allowed to take the characteristic function of that. The reason why is because there is such a tuple that satisfies this constraint. And when I have such a thing, I can take the characteristic function and know that the minimization of it is still an element of the general recursive functions. Okay, and so what I do is I define h hat here, which go ahead and finds the minimal d that encodes the sequence that I just mentioned. So for h evaluated at y, so the point is h evaluated at y, n1 up to nm, this defines a sequence, which is the sequence h naught, n1 up to nm, comma, dot, 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 comma, h, y, n1, dot, 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 nm. And then what h hat does is it calculates the natural number d, which is the least, such that it encodes this sequence. Okay, and then it's just a simple observation that in order to evaluate h at this input, at this index y with the input n1 up to nm, all I do is I construct this sequence and then read the yth element of that sequence. And that's exactly what this does. So I've got my bracket in the wrong place. Sorry, I need to rewrite the end. Okay, so what's happening there is I take h hat of this thing, which is the natural number that encodes that sequence, and then I read the yth element of that sequence, which is the final one, which is going to evaluate h at that index for me. Cool. So this shows me how I can use beta functions in order to mimic, sorry, not mimic, I can use beta functions in order to still get all of the general recursive functions, even if I leave out the primitive recursive clause. Okay, that finishes the proof from last week. So let me know if there are any questions whilst I move to the next board, and I'll get started on this week's lecture. The goal of today is to prove this big theorem that I've been mentioning all the way through this lecture series, which is that the general recursive functions are representable. I.e., if f is general recursive, there exists a formula f in Q such that if f of n1 up to nm is equal to k, then Q can prove f of n1 underline up to nm underline k underline. Oh, wait, no, that's not it. So, let me rewrite this. It's essentially that, but I actually need something a bit stronger. So for all y, f of n1 up to nm, y, if and only if y is equal to k underline. Okay, cool. And the way that we do this, well, we've actually done the hard part. The hard part was the reduction of the primitive recursive clause. So all I need to do is go through the definition of the simpler characterization of the general recursive functions, and then show that I can mimic that construction inside the system Q in order to construct the required formula F. Okay, so to get started with this, let me show you one of the base cases. So we had the zero function, we had the successor function, we had the projections, we had addition and multiplication, and then also the characteristic function of equality. These are all representable in Q. So to give you a very elementary example, let's start off with the zero function. So the zero function from n to n maps all natural numbers to the value 0. Now, the formula f that I'm going to take is just the formula that y is equal to 0. Okay? And so now what I need to show this, where f is just y is equal to 0. So I need to show that Q can prove for all y is equal to 0 if and only if y is equal to 0. Right? So that's obviously going to be pretty trivial, but I can show you the proof tree associated to it. So start off by assuming y is equal to 0, then I use implication, introduction. It's going to be my first one. So I discharge this hypothesis, and I get y is equal to 0 implies y is equal to 0. I do the same thing on the other side, y is equal to 0, and then I discharge it immediately. And I've got two copies of y equals 0 implies that y is equal to 0. This tells me that y is equal to 0 implies y is equal to 0, and y is equal to 0 implies y is equal to 0. So I can use conjunction, introduction. And then that is what the following is shorthand notation for. And then I can use a for all introduction in order to show that I've proven this for all y. Cool. So there's a clause to be checked for all introduction, but it's satisfied here because y was not any fixed variable. This does not occur freely in any place where it's not meant to. Okay.
Hey, well,
so yeah.
I think all the zeros like need to be like underlined zeros.
Yeah, if you want. So there's a small difference between this zero and these zeros, right? So the problem is I introduced I introduced a constant which I just labeled 0. So 0 bar, that actually means the constant 0, and I'm trying to avoid sentences like what I just wrote. But sure,
Oh, I suppose, yeah. Right.
if the opinion is that makes it clear.
Okay. Yeah, it's only supposed to be distinct from
this is meta notation. That's meta notation for the constant 0, and then this is a meta equality. So I'm not entirely sure it makes it clearer. But
yeah, I mean, more important is the distinction between that and the 0 that appears in your definition of the function z.
yes, yeah. So there's a 0 here.
Like, and I think for that very reason, that like the meta notation for the constant 0 and the constant 0 look the reason why the constant 0 looks too much like the fact that the constant 0 looks too much like the number that the actual number represents, like the way that we refer to that, is sort of the reason why I think usually people just stick with like 0 underline, stick with the meta notation, because it's
I see. Yeah, that makes sense.
Because it's clear.
Yeah,
But yeah.
sure. You know, to be honest, I'm not entirely sure I'm in the camp of it's great to make all of these things distinct at all different times, because they are context inferable and you can kind of use them as sanity checks. So I should be able to just write these zeros here and say the sentence, by the way, that usage of 0 is different to that usage of 0. And you look inside your skull and you tell me whether that makes sense to yourself or not. And if it doesn't, you ask a question. But if it does, then that's an appropriate sanity check. But anyway.
Yeah, I guess the only reason I stress it is the fact that it's very easy to get confused between like provability within Q and like meta provability about like what Q can prove and what Q can't prove, and it's just a sort of like getting confused between different usages of 0 is sort of like can like cause that problem later on. So of course, if like a viewer, if the sort of reader of this like already understands this distinction, then there's like no need to draw all the underlines. But like, but for the person that's sort of like not conscious of this distinction, then I think it's important.
You know, actually, if I could just very quickly, I would love to get your opinion on this because I'm trying to write these notes as well and make them as clear as possible. And sometimes I want to write a sentence like, we prove Q proves something. Do you think that this is clear notation or is that confusing? It's like, where's the meta theory prove that Q can internally prove F? That's what that's meant to say.
Yeah, I think I like typically try and just use like the Q proves F part as like the main phrase in that sentence rather than sort of saying something about it. Like I would just say like Q proves F because here's the proof or something.
Yeah, I see what you mean.
But I don't think there's a huge problem with we prove F. but I do like to.
I normally end
sort
up
of-
saying like we show Q proves F or something like that. I don't know. I
Yeah,
haven't worked out the perfect
yeah,
balance
that's
between. Yeah. Okay, let's move on to the next board. Okay, so that was very much just to get our feet wet, and all of the other base cases are equally as trivial to prove. There's something slightly, there's two trivial steps instead of one trivial step if you're going to prove that the characteristic function of equality is representable. That's detailed in the notes, and I think I want to move on to a less trivial example now. So let me move on to the inductive clauses. So I need to show that the composition of two representable functions is representable. Oh yeah, I'll present the proof in the simple case where the two functions are just from the natural numbers to the natural numbers, as opposed to from a product of natural numbers to the natural numbers. But the proof is adapted perfectly easily to the more general case. Okay, so the composition of representable functions are representable. So proof. First, I want to introduce the two formulas that represent F and G. Okay, and I'll give you the formula that I claim represents the composite. So it's pretty natural what you would say. It's just there exists Z such that phi G X Z and phi F Z Y. Okay, and now I need to show that this is representable. So say we have two natural numbers and say F after, oh wait, no, G after F of N is equal to N. It will also be helpful to have an explicit description of F of N. So let K be equal to F of N. Okay, we have by representability of F and G the following. Oh, whoops. Great. And then we just need to combine these in order to get a proof of this formula here. And I can just construct that proof tree for you. Okay, this won't get me all the way there, but I'll get started. Okay, I begin with a for all elimination. Wait, is that what I want? No, sorry. I want conjunction elimination. So I'm just going to use one of these implications to begin with, because don't forget the shorthand here.
Right, but that's not literally the first rule that you can apply to that formula because it's not a conjunction.
Right, so you want me to use a for all elimination first.
Yeah, or you could just double underline it and claim what formula you can get to.
Yeah. That sounds even easier. Actually, no, you know what? Because the next one's a full. Let's just do it properly. Full elimination. Oh, yeah. Thank you. Oh, no, I'm on the other direction. So I want y equal to k implies. Oh, sorry. I keep making mistakes. Okay. What I want to get to, I'm trying to get down to phi f of n k, right? So at the moment, I have this phi f of n y, but I know that that holds if and only if y is equal to k bar. So it's not surprising to suggest that Q is able to prove phi f n bar k bar, right? But if I'm going to do that, then the good choice for this for all elimination is to put a k here instead of just an arbitrary variable y. I could go ahead and use the y there, but then I have to use two equality eliminations, and there's no point in that. So let me just go back to this. Right, and now I can use an implication elimination along with the axiom that, or the equality axiom that k is equal to k. Cool. Okay, and then once I have that, I can combine this with the second provable statement in order to get out to a proof of this. But I'm out of space, so I better run to the next board. Okay. So first I do a full elimination, so I can then do a conjunction elimination. No, not a conjunction elimination, conjunction introduction. Because now I have a witness, which is k bar, for the formula I'm trying to prove. Okay, so I do an existence introduction. Oh, oops. Okay, and then I'm going to do a for all introduction. And show that we have this for all y. Okay, now it's simply a matter of removing these brackets, I suppose, but you have to make a decision as to how the brackets are implemented in the first place, because I didn't explicate that when I wrote down the original formula. So when I wrote down phi gh, not h, y, f. Yeah, the notes that I wrote had a different notation that I decided to use in the lecture, and that's always fun.
What's the different bracketings?
Yeah, that's what I'm trying to write out now. So the point is, I need those brackets, you see, because this is the formula that represents the composite, as I'm about to write down. Right? And then what I need is for all y, phi gf xy, if and only if y. Oh, why does this even have an x in it? Okay, there's no x there. If and only if y is equal to n. Right? So can you see it? I've got...
Wait, you're at phi gfy? Shouldn't there be two input things? This is phi gf ny.
Yeah, but n's a constant.
Right, but like phi gf is a formula for which you substitute two terms.
Yeah,
And
sure. So write it like that. So that's what the free variable x was there for. So we can go...
no, as in, well, how you wrote it, it's not x, it's n.
I don't want to write n. N represents...
Oh, well, sorry.
the...
That's what you wrote you wrote an n there in the formula. Maybe you meant to write x.
No, I need an n here. So let me write it out for you. Phi gf of xy is there exists z, such that phi f x z and phi g z y, right?
Yeah.
And what we need is if gf of n is equal to m, then Q can prove for all y phi g f n underline y if and only if y is equal to m underline.
Yep.
Does that make sense? Okay, so going back to what I have, I basically have that, but I've just got these brackets here, right? Whereas where I need them is here, right?
Uh,
Yeah, but that's...
like you also need them around the exist z.
Oh, sorry, yes, here. So that's where I need the brackets, right? But they're just not in the right spot at the moment. But that's not difficult. That's just a matter of coming up with a proof of the different bracketing from a proof from this. That's just going to come from swapping around your conjunctions that you have here. So from one you can prove the other just because, you know, you have... Okay, if I have...
I'm pretty sure you can get to what we want as a conclusion. I'm not sure if it's logically equivalent. I think what we have is stronger than what we need.
Really? Because... Well, what I'm trying to avoid is I would then, from here, unwind this whole thing to get down to the conjunctions, right? So I would get rid of the for all y by using a for all elimination, and then I would
Yeah.
use an existence elimination, but that rule is a pain in the ass, right? So I assume that there exists a representative, and then I use that on the right branch, and then manipulate until I find something that is independent of that witness that I introduced. But all that I would be doing on that right branch is stating that since I know f and brackets g and h, I can then infer f and g and h, and I can then infer g, and then I'll have a few columns of the same thing, but reordering the way that I unwound the conjunctions, and then I'll put them back together in the order that I need, which will simply move the brackets around. So that's a lot of work in order to just move those brackets around, and it's not the crux of the argument. So I don't want to run it out here. Yeah, but it's inside. It's inside.
I wanted to make a point about this because we went through a couple proofs like this, and I keep seeing this pattern of where you start with the premises, maybe like unwrap them a bit, move them around, but then you sort of wrap them up into some big formula, like the one you've ended with here. But then that thing you need to like turn it into something else. So, and to do that properly, you would need to like unwrap it again. So like, and then this sort of that need to like unwrap again and then rewrap sort of makes you want to omit those details. But if you actually, I'm pretty sure if you did the whole proof and then like, what is it called? If you like normalized it, I think you would.
Detour elimination.
Yeah. If you did detour elimination on it, you would get to a simpler proof that just starts with like the existential elimination that you were avoiding and doesn't have like the intermediate stuff.
Yeah, I have no doubt. I guess my attitude towards these...
It might
I
be
kind of
less
see
comprehensible, though.
Oh, sorry?
It might be less comprehensible, though.
Yeah, that's the point. Like, this is just the obvious thing to do, and then you get some tedious fact about bracketing or something.
I actually disagree. I think you've like introduced the problem with bracketing, and I think that like the most natural way to do it is to start with the like is to you got to show an if and only if. So let's show an implication, which starts with showing that if you've got this existential statement, then you can show y equals m, and you can arrive at y equals m by existential elimination, and like you existentially eliminate the existential statement, you replace Z with some whatever. You replace Z with itself, whatever, and then you derive that. Well, you've got phi f and Z, so Z must be K, and then using that you can derive that Y has to be M from phi G Z M. Like to me, it's completely natural and actually like quite directly uses the tools of the proof system like in the intended way, and I think it's sort of is a sort of natural way to do it, I think.
Yeah, sure. I mean, okay, to summarize, you're just saying to start using conjunction eliminations here so that you break down that implication to then get what you need in order to prove this implication and then introduce the quantifiers at the front, right? Which
Sorry,
is
could you
fine.
repeat that?
Oh, I'm just saying the only thing that I think you need to keep in mind is that this is what you have to start off with, right? Which is by conditional, which is fine, but it's not as simple as just proving this by conditional. So what I think that you want is your last move is a for all introduction. Your second last one is an existential introduction, right? And so now all we're trying to do
The
is
second last one is a conjunction introduction.
from the biconditional.
Yeah, because that's the universal quantification.
Yeah. Okay. But yeah, like I don't know. I don't really think there's canonical proofs here, right? I mean, yeah, like at this stage, you can just perform a conjunction elimination and then break down this biconditional and then start building it up again, which I think is what you end up with if you take the suggestion that you were just making. I don't know. I guess I don't know. Maybe I should have more of an appreciation for this, but to me, this is kind of like the proofs are cheap. Like I don't really care. I found a proof. I'm not offended that it was a bit inelegant, you know. But sure.
I think like the reason why I sort of recommend care in this direction is like you remember the first few proofs that like in the iteration of these notes where I think you are often like confusing sort of meta proofs about proofs in Q with an actual proof in Q. Like you were sort of reasoning about like, oh, well, in this proof I didn't like use any of these properties, so therefore I can like introduce a universal here or something. Like I think being too callous about it, I like sort of leads you astray there.
I'm not suggesting being lazy about it. I'm suggesting using derived rules, right? So I want to say something like this is a derived rule, right? And so you prove that this is a derived rule, and then once you've shown that that's a derived rule, you can then go ahead and use it. You know, now you can avoid this derived rule by just being smart about how you unwound your conjunctions in the first place. But I don't really.
Yes, I think I'm not talking about this, but also with in this scenario, I would characterize the sort of proof we're looking at as like getting to the first bracketing of that conjunctions, like when you could have just gotten to the second bracketing from the start. Also, I think, I mean, Dan made a comment about like sometimes using detour elimination can using the version of the proof that isn't detour eliminated can be more intuitively clear or something, because that's how like lemmas work. That's how we organize mathematical information here. I don't really think that this version of the proof sort of gets to an intermediate like heart of the argument kind of thing, and then like does after which you do some like logical cleanup. I don't know. In my opinion, I think the way that the proof system is encouraging you to do the proof uh, actually exposes like the like what's going on a bit more than this.
Yeah, so I'll repeat, I make no claim that this is in any way, shape, or form a canonical proof of what I've done. I believe it's a correct one, and I agree with you that that's important. But I haven't really concerned myself so much with the most elegant proof trees that you can build. But yeah, there might be an alignment with the system's intended use or something that makes the arguments more transparent and also.
I guess what I'm like turned off by is the sort of take all the premises of the proof, do universal elimination on all of the universal quantifiers to get to make the right choices, and then like smash that all together into one big conjunction, and then just argue that by the logic I already know, you can sort of like rearrange this into the conclusion.
I don't believe I have said that, and I don't want it to sound like I would say something like that. I am not saying it is okay to argue about your meta-mathematical intuition when you're constructing proof trees, right? That might help you construct a proof tree, but then you need to make sure it's correct. The way that I would make sure that it's correct is by using derived rules, possibly, or constructing a different proof. But I don't mean to say at any point that it is sufficient to just use your meta-theoretic intuition towards what a subsystem could prove. I would never say something like that.
Yeah. Okay.
Okay, cool. So now I want to get on to the last inductive clause, which is just minimization. This one's a bit difficult. So maybe I'll put the statement here, and then I can move to an export. Okay. Okay, and you actually do a meta proof by prediction on this one. So I need a further assumption that Q is consistent. So I'm going to say if Q is consistent, then the minimization of F is represented by the following. Oops. Okay, I'll step through this once I've written it. Okay, so this might look ugly, but it truly isn't. This is perfectly intuitive. So the minimization of f, this is the function that returns the minimal value y for which f of y x2 up to xm is equal to 0, right? So what we ask for is that indeed that does evaluate to 0, and then all this says is for all values less than y, we don't get 0, right? So what this says here is there exists a z such that w plus the successor of z is equal to x1, right? But yeah, that's fine. Yeah. This is saying if w is less than x1, then it's not the case that f evaluated at w, x2 up to xm, is equal to 0. Okay, does the formula and the statement make sense? Okay, let me sketch the proof over on another board. Okay, so there's about 1 million proof trees involved in this one, so I'll sketch the proof, but the details are inside the notes. I do use derived rules, and I have explicit proof trees of these derived rules, so they should be perfectly legitimate. But we need a few different lemmas. So the first lemma we need, basically, we just need to be able to get our hands on these variables that we're arguing over. So I'll argue about a variable w. I say that it's less than x1, and then it satisfies a property. But w is just a variable. I want to be able to say if w is less than, so if w is less than n bar for some n, then w is actually equal to 0, or it's equal to 1, or it's equal to anything less than n, right? And then I'm going to use this these facts about w in order to prove the negation of the function evaluated at w, comma x2 up to xm is equal to 0. Okay, so we need to be able to prove that. So the lemma is simply q proves for all w if w is, oh, actually, I need to write it out a bit. So this is an inductive, the proof follows by induction on the natural numbers that we're restricting our quantifier to, that our quantifier is bounded by. So the full statement is for n greater than 0, we have that q proves for all w less than n plus 1 bar implies w is equal to 0, or ... or w is equal to n. Okay, so that's the first lemma that we need. So this is, let me call that lemma 1. The second lemma that we need is the trichotomy axiom. Now this is in fact derivable. By the way, I just want to say one more thing about the previous line. So this less than is not part of our language, right? Keep in mind that the way that I've defined q is that we only had the function symbols, which were the constants, as well as addition and multiplication, and the successor function. So, and the only constant was 0, so the constant as well as those three function symbols. So we don't have a relation symbol, so this is not actually part of our language. So what this means, so a less than y, that's just shorthand. it's shorthand for what I wrote earlier. There exists W such that A plus the successor of W is equal to Y. Okay, so lemma 2 is the trichotomy axiom, and it is... Actually, it's probably confusing if I write it like that. So for n greater than 0, we have that Q can prove for all x is less than n, or x is equal to n, or n is less than x. Okay, so keep in mind that when we're trying to prove that a formula is a representing formula, we're trying to prove that for all y, and then our formula here, so it might be n1 and m bar y, if and only if y is equal to k underline. So the question is, how do we prove that direction, right? That direction's the difficult one because y is some arbitrary variable inside our language, and then I need to somehow deduce that it's equal to this constant, right? So the way that you would do that is you make use of the trichotomy axiom. We know that for all x, it's either that or that or that, and then the goal is to knock out these two possibilities by way of contradiction. So that's the way that we're going to use this lemma. Okay, and then finally, finally we prove the main proposition at hand, which is that the minimization of a representable function is representable. Okay. I might have to stop here, unfortunately. I'm feeling quite burnt out, quite tired, and also this is all very technical and not going to take a small amount of time. Is it a big deal if I leave it there? Can I just leave it there and save the
that's
details
great.
for next week? All right,
Yeah,
cool.
that fits the time anyway. Thanks a lot, Will.
Yeah, no sweat. Okay, that's it.
Thanks, Will.
Any questions?